Good morning, everyone. We're here this morning. Thank you for your time and your attention with this presentation. We're going to talk about the reduction of noise through composites. Myself, Reggie Offen, I work with Globe Plastics. This is my Rick Falk, and he's with Citadel Plastics. We work together on this project and this presentation. Where did it all begin? How did we get into sound at all? About in 1992, we got some contact from JBL regarding a two-part acrylic horn that they were designing. They had two-part machined acrylic with two steel inserts, and they were trying to reduce cost in the K2 model. So they came to us. We were able to do a molded composite enclosure with turning those four components into two components, therefore reducing cost and improving performance. Then again, a couple of years later, they came to us again with another problem that they were having, and that was they were using that two-part horn, and they were trying to see how could they then improve that two-part horn. So we took a two-part and we turned it into a one-piece horn with reverse angles. That's how, again, we found they had a problem, and we then gave them a solution to their problem. So now I'm going to talk a little bit about Globe Plastics and who we are. Globe has been in the molding industry since 1958. We've been committed to working with our suppliers and with our customers to create a synergy between all. We started out in the aerospace industry, and we're still in the aerospace industry. Aerospace is probably 50% of our business, but we started working with our material suppliers to see how we could find a way to convert some of these automotive and aerospace materials over into other industries, which would give them the benefit package that they were looking for. So we then started looking around to see how we could do that. We're a compression molder, we're injection molding, we do thermoset materials, thermoplastics. Most of our focus is in the thermoset industry. We do mold making, engineering services, and we have facilities in US and in Asia. Our molding capabilities are, we have 20 compression molding machines from capacity from 1 ton to 500 tons. We do transfer molding. Our platen sizes, the largest one is 48 by 60. We have 4 thermoset injection machines, thermoplastic machines, closed loop controls. I know some of you may not understand some of this thermoset stuff, so when Rick gets up here, he'll explain a little bit more about the thermoset side of the material aspect of things. We're an AS 9100 company. We utilize our same quality system throughout both commercial and aerospace. Therefore, everyone gets the consistent products through and quality all the time. Engineering support. This is one of the strengths that Globe has. A lot of times if you come to a company and you have a problem, they have to send it out for design work. Well, internally we'll take that, we work from the cradle to the grave with our engineering support. A lot of companies come to us just because of how we work with our companies with the engineering side of things. We'll look at the project, see what the problems are from the very beginning. If you have an issue, how can we improve that problem? What can we work on? Maybe you could change this angle. Maybe you could change some bosses or change ribs, and that really helps out in the end so that everyone comes out with the best product in the end of the day. We do structural analysis, solid modeling. We utilize SolidWorks, AutoCAD, and MasterCam for our computer systems. Some of the advantages of the AcoustaComp materials that we've developed for the audio field is no tinning, echoes. The materials are rigid and they're dense. High dampening properties, low Q provide efficient reproduction of sound. We minimize our bracing internally because of the density of our materials and their rigidity. Therefore, you reduce part cost. One of the things we do with part consolidation, I can remember back in the time someone came to us and they were utilizing a UHF horn, a panel, and a high frequency horn, 3 different part numbers. We took those 3 part numbers, consolidated them into one part, therefore reducing part number and reducing the amount of work that had to go into secondary operators for installation, therefore reducing installation cost. Design freedom with complex shapes. Because it is molded in, you have the ability to design, your design is open and you could design any way you would like, so therefore reducing Design time. More advantages of the AcoustaComp materials is their low material cost versus engineered thermoplastics. Engineered thermoplastics are high-end polymers. Polymers are controlled by the petroleum industry. That, as we all know, the petroleum industry is very volatile as it is today. It's down. Next week it might be up. The thermoset parts, although they're only 30% in the polymer industry, therefore we are price stable. High strength and high temp, because of our materials are dimensionally stable. They don't move around because they are a thermoset. Once they are cured, the temperatures don't affect our materials. From sub-zero temperatures up to 500 or 600 degrees, you don't see any movement on the parts. They're lighter than our materials are lighter than metals, and limited secondary machining operations, like you see in a die-cast part. Once the part's molded, you got to do a lot of machining. You got to do threads. You got to do afterwards. We mold in threads. We do all the secondary operations are as a molded part. Now I'm going to turn it over to Rick, and he's going to speak a little bit about materials, and then in the end of this, we're going to come in. Tim Gladwin's been helpful enough to do a little testing with us, and he's going to speak on some of the testing after we've done, so you can see how we've progressed from the materials, worked with the material supplier. Here the true synergy stepped in. I've worked with the material supplier, testing, and we've all come up with what we see is going to be an advantage for the sound industry. Here's Rick Falk.
So like a commercial.
I know, huh?
No, that's good. Hi. I'm Rick Falk. I'm the manager of new business development with Citadel. Citadel, we're a private equity firm, owned by a private equity firm. We're one of the only compounders who has both thermoplastic and thermoset capabilities. One of our principal owners is Steve Young, former quarterback of the 49ers, you guys may be aware of. Hasn't helped me with any football tickets or otherwise, but I'm hoping that one day it will. Our market participation, the sound industry is a small portion of our business. We're primarily in the electrical distribution and automotive. About 95% of the vehicles on the road today, our material is used for the headlamps or the parabolical configurations. We're also under the hood in electrical distribution. We're in residential and industrial circuit breakers, appliances. We're in handles. We're in vent trims on a lot of your refrigerator ranges. We sell approximately 140 million pounds a year into various BMC applications. The majority of what we're selling today is manufactured here in the U.S., with Asia and Mexico coming on strong. What is a bulk molding compound? BMC, a lot of people aren't aware of what BMC is. They look at thermoset materials as phenolic materials. They're black, they're brown, they can't be molded in contemporary molding fashions like injection molding. BMC is actually a very good material, very economical, and what gives it its advantages is BMC goes through an exothermic reaction when it's being molded. Converts it from a Play-Doh type material into an infusible solid state, which gives it its chemical resistance, its heat resistance, and dimensional stability. The components of BMC, as Reggie had mentioned, we're a very price stable material. 30% of our overall formulation is based on petroleum. That would be your resin package. The balance of that, let me back up. The resins are usually unsaturated polyester resin or vinyl ester resins, depending on your part requirements. We use shrinkage control. The shrink of our material is anywhere from 0 to 3. We also have mineral fillers in there. Mineral fillers, aluminum trihydrates, calcium carbonates or clays. That represents about 40 to 60% of the overall formulation. Oh, I'm sorry. And then we also have fiberglass reinforcement. Fiberglass reinforcement can range anywhere between 6 to 30% of the composite material, depending on your application. We have curing agents. The material is shelf life sensitive. The material has about a 60-day warranty period. Depending on the formula, it can last longer or shorter than that. And then it can also be pigmented. Unlike phenolic materials, which are typically black or brown, BMCs can be pigmented in any color you would like. We can also add granite appearances to the chemical composition. This is what the material looks like in its raw format. Up in the top, you can see it kind of looks like Play-Doh with fiberglass reinforcement in it. Has that same type of consistency. If you're going to injection mold it, that would be a typical format, or the shot over to the right-hand side. If you're compression molding it, we will cut it to exact length, diameter, and weight. So our overall value proposition of BMC is we're typically about 7 cents per cubic inch. Some materials a little bit more, some materials a little bit less, but you can see compared to die casting and some of the highly engineered thermoplastics, it is a great value. And you look at the applications where we're at versus some of the engineered thermoplastics, it's a very good material that a lot of people just aren't aware of. And I think that's all I have. It's my little infomercial. Tim?
There we go. So I talked to Reggie some time ago. I was looking for some information actually for my presentation on scanning enclosures. I wanted to be able to show how the Klippel scanning vibrometer was useful for determining enclosure vibrations. And I noticed that in their advertising, of course, they talk about how their materials are superior for vibration control. So I said, well, do you have any data? He says, no. Actually, he says we have some subjective data and some anecdotal data, but nothing really quantitative. And so that's great because I'd like to be able to show that I can give you that quantitative data. So this is what we did. We checked 2 enclosures. He graciously provided 2 enclosures. One was ABS, one was AcoustaComp, and they're both substantially the same. There were very minor differences between them, but they developed the AcoustaComp, I believe, to replace the ABS enclosure. And so what I did was I measured them both with the scanning vibrometer, which is a tool which can map the vibration on the surface of a object. And we measured the resonances and worked out. The Klippel tool is also capable of extrapolating the radiated sound power from the panel. So we compared that to the measured sound power radiated by the entire speaker. So the first thing we notice on this slide, at about 381 hertz, the ABS enclosure's got a massive resonance. And really we have to go to the cross-section view to see what's going on. And you can see that the amount of resonance is actually quite a bit. Sure. Am I able to move around with this? Okay. Oh, great. Perfect. So we can see that, we got the new technology. Oh, okay, got to get it the right way around. All right, so we had 284 nanometers of movement compared to 83. So that's 10 dB difference in the output off that side. And you can also see it here. At this frequency, we were at minus 70 dB, and this is in millimeters per volt, and minus 80 on the AcoustaComp. Sure. Let's go to the next one. Okay, go ahead and play. Yeah, we can play the video. So there's the ABS enclosure. This is a cross-section view of what's happening, and the AcoustaComp. So a major suppression of the vibration, 10 dB at that frequency. Okay, we can move ahead.
Question, why did you choose 384
So I looked at the mapping of it. If you want to talk later about it, I'll show you the actual data. And what we do first is we actually see a visualization of the vibration, and we export the curve. Oh, here we are here. But we generate the curves that show us where the peaks and valleys are, and we look. So I was looking for looking for a worst case, and you'll see that as we go further. We get to the sound power. You'll see where this came from.
I have a question, please. Were the wall thicknesses the same for the ABS and the AcoustaComp material?
Yes.
Yes. What is the specific gravity difference between the 2 materials, please?
I'm going to say that AcoustaComp is a 1.8 to 2.0, and the ABS is 1.04. 1.4. Glass build.
Yes, they will. Yeah. Yeah, we'll see that data. Yeah. So again, so you get a visualization of it. The visualization is nice to look at. It auto scales to use the full contrast range between the blue and the red. So from this view, they look comparable, but that's why we go to the cross-section views where I can actually measure it. Okay, so now we're at 955 hertz. So right from here at this point, so we get the transfer function at that point. And I'm picking the worst case at these frequencies. When you see the difference between these curves, you'll see the AcoustaComp overall is 10 to 15 dB on average lower than the ABS. So really, there's almost no point at which the AcoustaComp is even close to the ABS for resonance. So that's why I'm picking the worst cases. The 955 was a huge resonance, and there's about 25 dB of reduction when we go to the AcoustaComp. The AcoustaComp had no resonances anywhere near that level. So we can move ahead. There we go. So this is a curve that shows the sound power output of both, and this gives you the reasoning for picking those frequencies. The 955 is this resonance peak in the ABS, not visible in the AcoustaComp. So this is the sound power output from the side panel of the speaker. I measured one panel on the speaker, basically as being representative of the whole thing. The other side panel I would expect to be symmetric. And these are the largest surfaces on the speaker. The AcoustaComp, it's, I say 10 to 15 dB below. Not surprising, it's going to show some resonance features, but they're severely attenuated compared to the ABS. The 380 hertz region, both of them were fairly lively there. So that was a good comparison. And you can see that there you have a 10 dB reduction. You can see this is probably the same peak moved from the 955 to just over a kilohertz. But in this view, you can actually see why I picked those frequencies. I wanted to show really what's happening there. And this is how you start out. You look at the curves first and then look at the visualizations later. So this is the measured sound power of the speaker, measured all around the speaker using the Klippel near-field scanner. And so here you can see the sound power that's calculated from the vibration on the bottom of the curves and the measured SPL, or measured sound power at the top. You can see here we're about 30 dB down below the speaker. This is one side. The other side is symmetrical. You'll see a peak here that's up 6 dB. And you can see a corresponding feature ripple in the sound power. So this is a sound power curve. There's no diffraction effects, of course, in a sound power curve, which is why I like using them. When you go to the AcoustaComp, we don't have that feature in the 1 kilohertz range. So this is very typical of this kind of vibration analysis. You use it to find out what's happening on the panels, and you look for corresponding features in the sound power of the speaker itself. So we do this in reverse. When we get a speaker in or a design in that we see some issues in the sound power response or the SPL response that we weren't expecting, we then go back and look at the side panels. And yes, you'll start with your fingers and figure out which ones are worse, get the best, pick the best candidates for doing the analysis, and then we go ahead and do the analysis.
So as you can see, what we had here was Globe has been molding these components for years, but we knew we had something, but we didn't have the test data to back it up. So over the years, we worked hard on trying to figure out what could we do different to prove, yes, all the head engineers said, oh, your material knocks well. Man, this is really good material. So let's, well, can you tell us why you use it? Well, it's got a good knock test, so it must be good. Well, and the truth is, if I go out there and just tell you it must be good, you're going to say to me, prove it to me. And I'm going to say, well, just knock on it. Well, that tells you nothing. So what you need to do is you need to see some real test data. So what we've done over the years is we're working with our material supplier, trying to figure out different formulations, playing back and forth. And then finally, Tim came along and this really helped us out. And we now have something to prove. And we're planning on, moving forward to this. So if you guys have any questions, feel free to ask, and I'll try to direct them to somebody that can answer it besides me.
Hey, Reggie, I'm just curious with those two speakers, did you guys do some kind of subjective ABX type of test with them?
ABX?
Blind listening.
No, we just gave both components to Tim, same size, shape, form, and that's it. He need.
Yeah, I'm just curious if there was a perceived difference. You guys didn't listen.
Okay, so well, Tim didn't know. He was just looking for 2 enclosures. He wanted to test. If I could be wrong here, Tim. That you just needed some enclosures to determine whether your material, so you could test an enclosure. Whether our material came out better or not, we didn't know at all. We were just saying, okay, let's see how it works.
So I didn't have enough, I didn't care anything to solve. I was able to listen to test and want to equalize the speakers to be the same. I probably actually keep drivers, I have some drivers and or max those up. That's a much bigger program to go through. I probably look at the actual customer for these to see what their comments were on that.
It's interesting.
I don't know.
Because you have this big gap in DP resonating surfaces, I'm just curious how the
So,
ear would react to
I
it.
will tell you this, in other products where we've seen, not necessarily material changes, structural changes, and that we discovered in the vibrometer, and where the peaks and dips, sound power matches.
You want to
what we see on
give him
they're very odd.
just in case.
These are residents, your ear is very highly tuned, that kind of thing. These are actually very, even though they don't look like a TV or so, they're actually very sensitive to if they're a resident.
Over in Europe, one of the thermoset material has gained quite some traction is polyurethane. Have you got any experience with that in particular,
in terms of performance comparison with what you're offering?
Polyurethane?
Yeah, foamed polyurethane. So it's
Foamed polyurethane.
Foam. Okay. The problem with a foam polyurethane is you're not going to get. That's going to be a lower volume product. So what we're doing, we're focusing more on not a few products, a few horns at a time. This is more of a higher production realm. So you're going to get more if you need, hundreds or thousands of pieces as opposed to 1 or 2 pieces. So that's just what we're a molder of higher volumes. So we were trying to utilize what materials we currently have and how those materials could be utilized for the sound industry. As far as
I think you might be confusing foamed polyurethane with casting polyurethane in soft molds. I was talking about a material that also reacts inside a metal mold, these molds typically hold out for about 10,000 units. So it is also it is let's say a moderate to high volume process. So
yeah, no, we don't utilize those materials.
okay.
So we haven't done any testing on them.
All right. Okay.
Thank you. Yes.
Third question, Reggie. Did you compare the tooling, the complexity of tooling, and the cost of tooling between ABS and the AcoustaComp?
They're going to be very similar. The cost of the tooling is going to be very similar to AcoustaComp materials because AcoustaComp materials can be injection molded and compression molded. The tooling cost is going to be very similar.
So similar tooling materials and tooling life as well?
Yes, exactly. It's the same with the tooling is a little bit less than die cast, but about same as an ABS product.
Could you use an existing ABS tool to produce AcoustaComp product?
Yeah, depending on most of the time, yes, you just have to change the gate sizes or something of that nature because of the shrink factor, but most of the time you can convert those over pretty good.
All right, so if I already invested in certain parts and I want to switch, the switching cost isn't going back to the drawing board on tooling.
Well, we would have to look at the material it was first designed for, what that tooling was designed for, and then we could look at that.
Yeah, good.
Usually what you would do is instead of using water for the heating mechanism or cooling mechanism, you go in there with oil. But a lot of times, it's not a one-for-one trade-off. You'd have to do a heat profile on the tool to make sure that you're going to have adequate heat for the thermoset material. Where we're going, you're essentially taking a compound and you're heating it to get it to cure, whereas a thermoplastic, you're sharing it, you're creating a lot of heat, it goes into the tool as a fluid, and then it, for the most part, it cools to solidify. So there's a little bit of heat consideration that has to be, looked at.
Question right here.
The cost difference between those two enclosures and ABS and AcoustaComp?
cost difference between the ABS and the AcoustaComp. The ABS part is going to be less expensive as far as the finished product. I don't know price per pound on the two. And typically that's why people will go with the thermoplastic, because they're looking for the cheaper final product, cheaper for lower cost.
Yeah, I was looking for like a percentage, like if you're
Right.
getting a premium product,
10 to 15% maybe.
10 to 15, that's good.
Question, yeah, here you go. I'm probably loud enough, but let's be honest. Oh,
Just don't yell at me.
Hey, does the material allow for the same amount of ribbing as
You do not need as
normal
much
ABS?
ribbon.
We
No,
don't need as much, but does it
no.
allow for it? Say if it's a larger structure and you still need to add ribs to it.
Yes, you need to add some ribs, but not nearly as much as an ABS because of the rigidity and the density of these materials. You do not need to add as much ribbing. That's one of the advantages of these materials.
But the tooling still allows for different thickness areas. Do you have to deal with sink and other?
Well, I'm glad you asked that question. I didn't pay you, did I? The ribbing, like in a thermoplastic part, and when you have ribs, you get a lot of sink marks. These materials, you don't get the sink marks. That's an advantage because in an ABS, when you mold those, you'll start to flow around the rib, and then the surface will have those imperfections where you're flowed and you have sink. These materials do not get sink marks. They're very limited on the amount of sink that's involved in these.
It's a very low shrink material.
Yes, here you go.
In the analysis of it, did you guys get a chance to look in the time domain in like a waterfall part just to show the difference in the decay of the materials?
No, I didn't, sorry.
That'd be really cool to see.
More questions?
Rev 2.
Everybody good? Any more?
Okay, thank you guys. I appreciate your time and appreciate your patience.
Thank you for coming. Appreciate it.